Welcome to This Explainer. Today, we're diving straight into the fascinating universe of chemical solutions. We're going to move way past the basic building blocks and decode the complex and sometimes totally rebellious laws that govern how substances mix. Let's unpack the exact rules of the mix.
We've got a really clear roadmap for today. We'll start with the anatomy of solutions, move on to measuring solution concentration, cover the laws of solutions, explore when solutions break rules, and finish up with colligative properties explained.
All right, Section 1, the anatomy of solutions.
So the fundamental mechanics of mixing are actually all about limits. A solution is just a homogeneous mixture where a solvent, that's the substance doing the dissolving, takes in a solute. At first, it's unsaturated and hungry, meaning it can easily dissolve more. But keep adding solute, and eventually you hit a saturated solution. That is the absolute limit of what can be dissolved at that specific temperature. Now, if you force the issue by tweaking the temperature or pressure, you can actually create a supersaturated solution. But it's highly unstable. Eventually, those extra particles are just going to crystallize and fall right out of the mix.
You know, when we hear the word solution, we usually just picture a solid dissolving in a liquid, like salt in water. But there are actually 9 different types of solutions based purely on physical states. If your solvent is a gas, you can dissolve another gas right into it. That's exactly what the air we breathe is. You can even have solid and solid solutions, like brass, which is just a mix of copper and zinc. The rule of thumb here is that the state of the solvent always dictates the final state of your solution.
Moving right along to Section 2, measuring solution concentration. Here's where it gets interesting, because we need to contrast our 2 heavy hitters, molarity and molality. Molarity measures the moles of solute per liter of solution. It's incredibly common in labs, sure, but it has a massive fatal flaw. It changes with temperature. Because the physical volume of a liquid actually expands when heated and contracts when cooled, your concentration technically shifts. Molality, on the other hand, measures moles per kilogram of solvent. Since mass doesn't change with temperature, molality is completely temperature independent. So when thermal stability is absolutely crucial, molality is your go-to.
Of course, depending on the context, we have a few other specialized tools. For instance, parts per million is perfect for measuring incredibly tiny amounts, like trace pollutants or the fluoride in your drinking water. And keep your eye on mole fraction. It is exactly what it sounds like, the ratio of the moles of one specific component to the total moles in the entire solution. Keep that in your back pocket because it's the natural variable we're going to use in just a moment when we tackle partial pressures.
Which brings us to Section 3. The laws of solutions.
Back in the early 19th century, William Henry formulated this law dictating exactly how gases behave when they're pressured into liquids. He discovered a pretty brilliant rule. You can force a liquid to hold way more gas simply by pushing down on it with that specific gas.
Think about it like a piston. At low pressure, only a certain amount of gas is going to dissolve in the liquid below. But as you actively increase that partial pressure from above, literally pushing down, more gas molecules are forced into the liquid phase just to maintain equilibrium.
And Henry's law isn't just dry textbook math. It is literally the reason your soda fizzes. When you crack open a bottle, you release that high pressure, which drastically lowers the solubility of the carbon dioxide, so it rapidly escapes as bubbles. It's also why deep-sea divers breathe oxygen mixed with helium instead of nitrogen. Helium is much less soluble under extreme underwater pressure, which prevents dangerous bubbles from forming in their blood. And hey, if you've ever felt lightheaded climbing a mountain, that's Henry's law too. Lower atmospheric pressure means less oxygen is dissolving into your bloodstream.
So that covers gases, but what about volatile liquids? Well, enter François-Marie Raoult. Raoult's law gives us the baseline rule for how volatile liquids behave when we mix them together. In plain English, the more of a solvent you have in a mixture, the more its specific vapor is going to contribute to the total pressure above the liquid.
Think of ideal solutions as the law-abiding citizens of chemistry, represented by perfectly straight lines on a vapor pressure graph. In an ideal solution, like a mixture of benzene and toluene, the molecules basically treat each other equally. The intermolecular forces between the different molecules are virtually identical to the forces between their own kind. Because there's no preference, no drama, they mix perfectly. They follow Raoult's law across all concentrations without releasing heat or changing their total volume.
But, as we'll see in Section 4, when solutions break rules.
Because in the real world, not everyone follows the rules. While ideal mixtures mix perfectly, non-ideal mixtures are a lot more complicated. They form molecular cliques. If the different molecules don't really like each other, they interact weakly and try to escape into the vapor phase as easily as possible. We call that a positive deviation. But if they really like each other, They interact strongly and refuse to vaporize. That's a negative deviation. Because of these strong or weak interactions, mixing them will actually absorb or release heat, and the final volume might literally be slightly more or less than the sum of its parts. Mind-blowing, right?
And these non-ideal deviations can get so extreme that they create something called an azeotrope. An azeotrope is a highly rebellious mixture that acts stubbornly like a single pure substance when it boils. The vapor boiling off has the exact same composition as the liquid left behind. Because of this, you absolutely cannot separate them using normal distillation. They are permanently locked together.
These deviations lead to two extreme outcomes. Positive deviations create minimum boiling azeotropes, like a 95.6% mix of ethanol and water. That is the absolute limit of standard fermentation and distillation, because the mixture literally boils at a lower temperature than either pure water or pure ethanol. On the flip side, negative deviations create maximum boiling azeotropes, like a 20.2% mix of hydrochloric acid and water, which boils at a higher temperature than either of its pure components.
Let's wrap things up with Section 5, Colligative Properties Explained.
These four colligative properties are incredibly unique. Why? Because they depend purely on the number of solute particles dissolved in the solvent. They completely ignore the chemical identity of the solute itself. It does not care if you dissolve salt or sugar. If you have the exact same number of particles, you will lower the vapor pressure, raise the boiling point, lower the freezing point, and increase the osmotic pressure by the exact same amount.
But wait, there is a catch. To accurately calculate these properties, we absolutely have to use the Van't Hoff factor, which is represented by the letter I. Think of it like this. If you dissolve sugar, one molecule stays one single particle. But if you dissolve table salt, sodium chloride, it literally shatters in water into two distinct ions. So 1 unit of salt actually gives you 2 particles in the solution. The Van't Hoff factor mathematically corrects for this dissociation, making sure our colligative property calculations are always spot on.
Ultimately, the rules of the mix govern the physical world all around us. Understanding colligative properties like freezing point depression is exactly how we formulate antifreeze to protect our car engines in the dead of winter. And mastering azeotropes is how chemical engineers design those massive industrial refineries. It really leaves us to wonder, as we continue to manipulate matter at the molecular level, how else can we harness these precise deviations and colligative properties to solve tomorrow's macroscopic engineering challenges? Thank you so much for joining me on this deep dive into solutions. Keep questioning and keep exploring.